This is a total production. Alright, Chem Minions, this is going to act as our third Chapter 6 practice video. There will be more after this. They'll be labeled Part 2. But with this practice video, this one is all about hydration reaction. So when you think hydration, you should be thinking water. So more or less, all of these reactions are going to add, these are addition reactions, they're going to add water across a pi bond. Now, what that means is one carbon will get an OH group, and then the other carbon of the alkene most likely will get the hydrogen. All right. Now, depending on the three different hydration reactions we have, there could be an extra step or a layer of complication. So, for instance, a lot of times, if you ever see hydronium, H3O+, you need to stop and think about the mechanism of this reaction. Okay, the other two, we don't really focus on the mechanism. We just talk about them in terms of being Markovnikov additions or anti-Markovnikov additions. And at least for the first iteration of them that we see in this practice, I'll go over with a generic view of the intermediate. But if we look at the hydration reaction, what you're going to see here is, yet again, your alkene's going to act like the nucleophile. It's going to take a hydrogen off of hydronium, right? And you're going to get this first intermediate. There's going to be multiple intermediates, right? So firstly, let's look. We're going to get a carbocation out of this, where a hydrogen is either going to go here or here. And we know that if a carbocation's formed, we're going to make the more stable one. So we're going to get a positive charge there because the hydrogen went there. All right. Now, remember, carbocations can undergo rearrangements because carbocations are like spies. They're always looking around, keeping up with their environment. What's going to happen next? Oh, do pray tell. So, what we're going to see here is a rearrangement in the form of a hydride shift. So we're going to get a plus charge right there now to get that more stable tertiary carbocation. All right. Now at this point, what you're going to see is water can attack, right? Because this is hydronium's been deprotonated. So now water can attack, right? Because it's got a lone pair on that oxygen. So what are we going to get? We're going to get water attacking a trigonoplanar carbocation. So it can attack from either side. OH, right? And so I'm elaborating on this bond right here because the oxygen has a positive charge and it needs to be alleviated. Now, what's the other problem here? This is a chiral center now, right? Isopropyl, ethyl, and a methyl, and then OH, water, right? So what you're going to see happening here is a second equivalent of water will come in and deprotonate that guy, because in this case, hydronium is acting like a catalyst, so we got to regenerate it. So let me move over a little. So we get OH, and then of course hydronium, right? But remember, I said that when this attacked, it attacked a trigonal. This is a new chiral center. So we're going to have to now in the products. I'm going to worry about stereochemistry. So I'll start with one alcohol as a dash plus its racemate, right? Because we're going to have a racemic mixture where I'm going to put a wedge on the other alcohol. So these are the two products we would make. Okay. Now, hydronium is the only one that's going to give me this racemic, for hydration reactions, are going to be the only one that's going to give me a racemic mixture option, right? So when I use mercury or when I use boron, I'm not going to worry about any type of racemic mixture option. Okay. Now also these don't undergo rearrangement either because I don't form a carbocation. So like for the mercury here, the way it works is that you actually get this kind of weird intermediate here, and I'm not going to draw it every time, but you're going to get this weird intermediate where you get this three-membered ring with mercury and one of those OX stays on. And so then the water comes in and attacks that position, right, to kind of kick the mercury off. And then that'll all get deprotonated and stuff. So what you're going to get here is that specific alcohol. All right, so it didn't undergo rearrangement, and it stayed with one of the two original carbons of the alkenes. All right, so anyway, the sodium borhydride is kind of what helps get rid of the extra hydrogen and helps kick the mercury off. All right, so every time we see mercury, we need to think that it does a Markovnikov addition. Okay, so that means it's going to put the OH of these two carbons, it's going to put it on the more substituted carbon, right? So that one right there. Okay, now hydroboration, using boron here, it's the exact opposite. It does an anti-Markovnikov. All right, and a lot of that happens because the boron lines up due to sterics. The boron will actually line up with that carbon, and then one of the hydrogens will line up with the other carbon. So because this carbon's more substituted, so it's more crowded, so this hydrogen here is going to line up. So it'll make this weird kind of square looking intermediate. BH, right? Something like that. And then this peroxide comes in to kick the boron off and break that hydrogen. So the BH2 here, so this and this go, and the carbon here gets a gets an OH. We kind of, it's just kind of common to just skim through it, and so you can kind of see here, right? The OH went at the end, right? The less substituted carbon of the alkene, right? This carbon right here. And so that's why this is called anti-Markovnikov, right? So just remember, Markovnikov means put the OH at the more substituted carbon. Anti-Markovnikov, put the OH at the less substituted carbon, okay? And so yet again, here we go. This is going to do the hydronium, so we're going to have a carbocation intermediate. And I'm only really going to show you in this case the carbocation that forms, which would be that, because we would make the more stable one. So that's tertiary. So there would be no rearrangement that would happen. So then you would have your water attacking again, right, like so. And then right, so you have water there. And from there, a second water molecule comes in to take one of these hydrogens. So what you're going to get is your Markovnikov alcohol. Now also remember, right, this had a carbocation intermediate, so when that water attacked, we did make a new chiral center. So I do have to worry about stereochemistry for this. So I'd have one where I have a dash on the alcohol, and then I have another one where I'd have a wedge on the alcohol, like so. All right, so that's what we're looking at for these products, okay? Next, we have another mercury option, and remember, mercury does Markovnikov, right? So that means of these two carbons, where's the OH going to go, right? We're going to see the OH go there, and we're going to see the hydrogen go there, right, when we hydrate it. So that will be the products that I'm going to look for. OH, right, like so. Okay. Mercury adds the water, right, in a Markovnikov addition. OH is at the more substituted carbon. Now the BH3, this is anti-Markovnikov. Right, and so when it lines up, that means it's going to put the OH at the less substituted carbon, right, which would be this one. So you're going to get OH here, and you're going to get H there, okay? So that product, right, because it's an addition, so the pi bond disappears. All right, so it looks like that. Oh, no, I wrote that wrong. Sorry, y'all, got to rewrite it. Right, so it looked like that. There's my alcohol. I don't know why I wrote the H so high, but there it is. Okay, so this would be my anti-Markovnikov product. That would be my Markovnikov product. All right, and then next up on this guy, right, we're going to get pi bond attacks a hydrogen. All right, so when we make the carbocation, we should have a plus charge here. All right, then that means we're going to have water coming in, attacking that position. That is a trigonal planar carbon. And then I'm also going to just go ahead and say then we're going to deprotonate. So I'm going to take a hydrogen off that guy. So the products we're looking at for this, right, you're going to have an OH there. That's a new chiral center. So I'm going to need to worry about showing that racemic mixture of products. 1, 2, 3. Like so. Alright. So there's that product. I ran out of page, so I had to scrunch it up a little bit. Alright, and then looking at this one, so that didn't undergo a rearrangement because if you look, that would be a primary, that would be a secondary, so there's no real reason to rearrange. And so the hydronium reaction and the mercury reaction, those products are going to look the same because this is a Markov-Nikov addition, right? So it's when we look at what gets added, right? One carbon gets a hydrogen, the other one gets an OH. Markov-Nikov means the OH goes at the more substituted carbon, right? Like so, and then that pi bond's going to disappear. So for the mercury, we're going to get that, okay? And we don't worry about showing the stereochemistry on this one, so just remember put the OH there. All right. Now with hydroboration, when you have boron and you have peroxide, this one always does the anti-Markov-Nikov, right? And so that means when we look at these two carbons, right, anti-Markov-Nikov means OH goes to the less substituted carbon. That would be this one right here. So OH there and then H there. So our anti-Markov-Nikov product would look like that. Okay. Hopefully this was beneficial in you kind of seeing a few different instances. You notice the only one we really worry about stereochemistry in terms of, do we get a chiral center in our product is with the hydronium. We also notice that it's the only one that undergoes a rearrangement. Okay, while with mercury, we just think Markov-Nikov, put the OH on the more substituted carbon. With hydroboration, right, we always think put the OH on the less substituted carbon. And that's it, anti-Markov-Nikov right there. Okay, so anyway, adios and stay weird.